Ready for a wild ride? Today, we're going deep, like really deep, into how life on Earth even got started.
Always a good place to start,
Yeah.
right?
And the coolest part is, it all comes back to, get this, meteorites.
Meteorites. Space rocks with a story to tell.
Totally. And the stories these meteorites are telling are blowing my mind. We're talking about the building blocks of life here, the actual ingredients. It's incredible.
Yeah.
Luckily, I didn't come alone.
Glad to be along for the ride.
You're our cosmic tour guide today, ready to break down the science behind all this. So, should we rewind the clock a bit? I mean, we're talking billions of years ago, right? Back when our solar system was just a baby. What was that whole scene like?
Picture this.
Yeah.
About 4.6 billion years ago, a swirling, chaotic cloud of dust and gas. Gravity's the director here, pulling everything together. And within this cosmic whirlwind, tiny particles are bumping into each other constantly, sticking together.
Yeah, so far so good.
In these little clumps, they start combining too, getting bigger and bigger, forming what we call planetesimals. Think of them like the seeds of planets.
Planetesimals, so like those building blocks we talked about. But instead of Legos, we're talking about, well, planets.
You got it.
But we're not just interested in rocks in space, right? I mean, the real prize here, the real mystery, is how did life itself get started?
Absolutely. And that's where things get really interesting, because to crack that mystery, we need to talk about an element that doesn't usually get a lot of fanfare. Zinc.
Zinc, like the stuff in vitamins.
The very same. Turns out, zinc holds some crucial clues. By analyzing the isotopic ratios of zinc in meteorites,
Whoa, hold on a second. Isotopic ratios, that sounds a little intense.
it's all about looking at the different versions of zinc atoms, which have slightly different weights. By comparing these ratios in meteorites to what we find here on Earth, scientists can figure out where those meteorites originated way back in the early solar system.
This is like a cosmic fingerprint for each meteorite,
Yeah.
telling us its address in the early solar system.
Exactly. And zinc is particularly good at holding on to that memory, making it a reliable tracer, especially for something as tricky to track as volatiles.
Volatiles. Okay, now you're just using big words to make me feel small.
Sorry, volatiles are simply elements and compounds that evaporate easily, like water, carbon dioxide, things like that.
Ah, okay, so the essential ingredients for, well, pretty much everything on Earth. No pressure, zinc, but you're kind of a big deal.
You could say that, because without volatiles, you don't have an atmosphere, you don't have oceans, and you definitely don't have life as we know it.
So the researchers, they use these zinc ratios to figure out where those all-important volatiles came from. And did those planetesimals we were talking about earlier, did they play a role in all of this?
They did, and here's where the research gets really wild. They found that in the early solar system, there were actually two main types of planetesimals, each with a very different story. So imagine those planetesimals that formed close to the sun getting blasted by that intense heat.
Like way too close for comfort, right?
Definitely. And all that heat, it would have melted them and boiled away a lot of those volatile elements we talked about, like water and carbon dioxide.
So they're like those cosmic popcorn kernels I mentioned, all puffed up and empty inside.
That's a great analogy. These we call the melted planetesimals.
Makes sense.
Now, farther out from the sun, where it was much cooler, you had the unmelted planetesimals. They held onto their volatiles.
So they're like the cosmic ice chests, still full of all the good stuff.
Exactly, full of those essential ingredients for life.
Okay, I'm seeing two very different types of space rocks here. So how does Earth fit into all of this? Which ones ended up becoming part of our planet?
Well, get ready for this. This is where the zinc analysis gets really mind-blowing. Those melted planetesimals, the ones that lost their volatiles.
Yeah, the cosmic popcorn.
Right. They actually make up a big chunk of Earth's overall mass, about 70% in fact. But here's the kicker. Their zinc isotopic signature, barely there.
Hold on, back up a second. You're telling me that most of Earth's zinc, which we know points back to those volatiles, didn't come from the melted guys?
You got it. The data is telling us that the vast majority of Earth's zinc, and by extension its volatiles, came from those unmelted planetesimals.
That's wild. So even though they make up a smaller portion of Earth's mass, those unmelted planetesimals were the ones that really brought the life-giving ingredients to the party.
It seems that way. It really makes you appreciate the importance of timing and location in those early days of the solar system, doesn't it?
It's not just what you're made of, but when and where you were made. And to have a planet that could support life, getting a healthy dose of those unmelted, volatile, rich planetesimals seems like it was crucial.
Absolutely. Those unmelted planetesimals were like the ultimate delivery service for the building blocks of life.
This is making me look at meteorites in a whole new light. They're not just space rocks. They're like time capsules from that early solar system.
That's exactly why this research is so exciting. And it's not just about looking back in time, it's about understanding the potential for life beyond Earth, too.
Because if it happened here, why not somewhere else, right?
Exactly. And it opens up a whole new world of possibilities for where we might find life out there in the universe.
Mind blown. Okay, so we've journeyed billions of years back in time, explored the wild early days of our solar system, and we've seen how crucial those unmelted planetesimals were in bringing us the ingredients for life. But this is more than just an origin story, isn't it? What does this all mean for how we understand life itself? This is huge. It's like we've been so focused on finding another Earth, a planet that looks exactly like ours, with the same history, the same ingredients, but this research is telling us to think bigger, right?
It definitely throws open the doors to a lot more possibilities. Like, what if we've been a little too narrow in our search for life beyond Earth? We've been looking for planets with liquid water, a breathable atmosphere, a nice stable orbit around a star like our sun.
All the things we know and love here on Earth.
Exactly. And while those are all still important factors, this research is suggesting that the type of material a planet gets early on, those building blocks we were talking about, and when it gets them, that could be just as critical for life to emerge.
So instead of looking for Earth 2.0, a perfect mirror image, we should be open to planets that, I don't know, maybe took a different route, a different recipe.
Exactly. Planets that might have incorporated different elements, different amounts of heating and cooling, maybe even got their volatiles from entirely different sources than Earth did. Planets that might completely change how we define a habitable world.
It's like we're so used to our version of the recipe for life that we forget there might be other ways to bake that cosmic cake.
And who knows? Those other recipes might lead to even more incredible and diverse forms of life than we can imagine. It really challenges us to expand our perspective and be open to the unexpected.
So we're not just looking for signs of life as we know it anymore, but life as we don't know it. That's both exhilarating and a little intimidating, isn't it?
It's definitely a reminder of how much we still have to learn about the universe and our place in it, but it's also incredibly exciting. Every new discovery, every new piece of data brings us one step closer to answering that fundamental question: are we alone?
This whole deep dive has been mind-blowing. From the chaotic birth of our solar system to the surprising role of those unmelted planetesimals, we've really uncovered a whole new understanding of how life on Earth, and maybe even life beyond Earth, got its start.
It all comes back to those cosmic building blocks, those hidden connections between our planet and the vastness of space.
And the best part is, we're just getting started. So to everyone listening, keep your curiosity burning. Keep those telescopes pointed skyward, because the universe is full of wonders just waiting to be discovered. Until next time, keep exploring.